Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. As always, the goal of the seminar series is to bring the community together. Our seminars stream live on the third Thursday of every month at 11 a.m. Eastern. They're also available to watch anytime on the YouTube channel. We've had an absolutely amazing group of speakers as part of the seminar series over the past several years. And again, we encourage you to check them out on the YouTube channel anytime. We also have a great group of speakers planned for the upcoming months, and we hope that you will join us for all of them. Before we get started, a few quick thanks. Dr. James Batiste, the Center's Director, Jennifer Belsick, the Center's Administrative Coordinator, Dr. Frankie Antolon, the Director of Outreach and Education, and two CMCC students without whom the seminar wouldn't be possible, Ryan Kwok and Brian Hilsbeck. Please do continue to follow us and join us for our upcoming seminar series, all available on the YouTube channel. A few quick guidelines. The webinar is being recorded. If you have questions you're watching live, they can be emailed to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube channel. Either way, they'll be propagated to the speaker at the end of the seminar. Lastly, we would love to hear from you. If you have any feedback on the seminar series, suggestions for improvement, please do let us know, and we'd be happy to incorporate them as we move forward. Last but not least, it's my great pleasure to welcome today's seminar speaker, Professor Orla Williams. Dr. Williams is an assistant professor in the Advanced Manufacturing Research Group at the University of Nottingham. Her current research focuses on biomass processing for bioenergy, mechanochemical extraction, as well as life cycle analysis of manufacturing processes and energy efficiency of buildings. Her Anne McLaurin Research Fellowship investigated sustainable biomass-based processing techniques to produce critical raw materials for the circular economy. Dr. Williams was awarded an engineering doctorate from the Efficient Fossil Energy Technology Center at University of Nottingham, where she focused on milling optimization for bioenergy. Before starting her doctorate, Dr. Williams completed a master's degree in mechanical engineering from the University of Bath and worked as a chartered building service engineer for Burrow Happold Consulting Engineers in Bath and Los Angeles for several years. She has also worked as an engineering drawing archivist for the Snowdon Mountain Railway and an environmental engineer at Rolls-Royce Defense Aerospace. She's on the editorial board of the Elsevier journal Biomass and Bioenergy, and a committee member of Fuel and Energy Research Forum in the UK. It's our great pleasure to welcome Dr. Williams to Mechanochemistry Discussion Seminar Series.
Hi, my name is Dr. Orla Williams, and today I am going to be presenting you a talk on optimizing milling for mechanochemistry. I'm an assistant professor at the Department of Mechanical Materials and Manufacturing Engineering at the University of Nottingham in the UK. The University of Nottingham is an award-winning campus in the UK, China and Malaysia, so we are a tri-campus university. And we are one of the founding members of the UK Russell Group and global network of Universitas 21. We have 50 global teaching partnerships plus study abroad agreements with over 175 universities in the world, and research collaborations with over 6,500 institutions. We have more than nearly 350,000 alumni and living in 195 countries. And there have been 2 Nobel Prize winners from our university, Sir Peter Mansfield for MRI scanners and Sir Clive Granger for economic forecasting. We are ranked first in the UK for graduate careers and top 3 for universities for working with business. We're also 7th in the UK in terms of research power, so this is based on the impact of our research. We're actually 3rd in the UK for engineering, and we're in the top 20 rankings in the UK in the QS World Rankings, and top 100 university for the QS World Rankings as well. So we have quite an extensive history of milling at the University of Nottingham. This primarily comes from coal research. Nottingham is a very coal area. We had a lot of the coal-fired power stations were in this region. And there were a lot of coal mines in this area. And this meant the university did a lot of coal research since its founding in 1948. However, since coal is no longer being used in the UK for power generation and our steel industry has declined, we are now focusing more on researching low carbon fuels and moving away from coal dependent technologies. We have extensive milling facilities for material processing at the Faculty of Engineering, and we recently received a large donation of milling equipment from Uniper. Uniper is the company that owned Ratcliffe-on-Soar coal-fired power station, which you can see here on the right. And this was the last coal-fired power station that operated in the UK, and it shut in 2024. However, there are other coal-fired power stations, for instance, Drax and Linemouth, which have been converted to use biomass. And a lot of the research that we've done over the last 25 years has been looking at how moving from coal to biomass and understanding what that change in the material has meant for reusing the existing equipment, what modifications need to be done, and how those challenges can be overcome. So we focus on understanding the influence of comminution on different processing techniques. So my own personal experience, as I mentioned, I'm an assistant professor in mechanical engineering at the University of Nottingham, but I work closely with our chemical engineering department. My PhD itself was on biomass milling for power generation. So this was trying to understand how different types of biomass work in different, or break down in different types of mill. And as you can see from the little video on the bottom right, this is from something called a split Hopkinson bar, which is used to calculate the dynamic stress and strain of materials. So what you have is basically a gun which is launched by compressed air, and we have these perspex bars with strain gauges on either side, and it measures the impact of the material. It measures the strain, the transfer of the energy, and from that you can work out its stress, strain, and Young modulus. So this gives us information on what happens during impact collisions at high speed, which you can see obviously relates towards milling. So we also do extensive work with industry on millings to address their issues. We work a lot with power generators to understand new fuels that they are looking at and how they behave compared to what they currently use. And the work focuses on greater understanding of milling processes and linking those actually back to their material properties. So current milling processes are very, very energy intensive. On the right, we have two mills from coal-fired power stations in the UK. So what we have is a tube and ball mill here at the top. So that's probably the closest it's to sort of the planetary ball mills that we see a lot in mechanochemistry. And at the bottom, we have what's called a ring and roller mill. A ball and race, and that's from Drax. Now, these are continuous throughput mills at scale. So these can get through a huge amount of tonnage per day of different materials, and they're used, they're continuously inputting and outputting the materials. And the process that they're trying to do is comminution. So that's reducing solid materials from one average size to a smaller size by crushing, grinding, cutting, or other mechanical means. Now, milling accounts for 2 to 3% of the total worldwide energy consumption. I think it's only just currently, which is one of the biggest for any one process in the world. I think it's only recently been overtaken by data centers for AI. But comminution accounts for around 50 to 70% of the energy used in material and mineral processing. And when we're looking at full-scale operations, minimizing this milling energy has a real impact on the economic viability of using different fuels, for instance. If the energy you consume is 2 or 3% of the energy within the material, then it's a poor option. So if there are ways of reducing that energy consumption, then it means that you can make that material a more economically viable for different applications. So to give you an idea about bioenergy in particular, it provided around 15% of all of the UK's electricity in the UK in 2024. This primarily comes from Drax, which is the largest power station in Europe. So they have I think it's 600 megawatt boilers on there, and 4 of them have been converted to run at 100% biomass. So that's 2 gigawatts of power. And that, though they use over 8 million tons of wood pellets a year in pulverized fuel combustion. So that 8 million tons of wood all needs to be milled into a fine powder for combustion. So this is around 20% of the global wood pellet is basically going to one power station. Now, they are actually one of the world's largest producers of pellets now, as well as the largest consumers. But you can see, optimizing this process is vital to the viability of these plants. So what happens in these mills? So this is what's called a ring and roller mill. This was from West Burton Power Station, which did use different types of biomass and coal. But you can see here what we have is the rollers at the base, and there's like a flat plate here. And these turn and roll around. We also have down at the bottom, we have incoming air that comes from the bottom, and that will lift the particles up through the mill and out. So we can see a little animation of it here. We have the actual coal or your material falling into the mill. It's too heavy to be raised at the moment, so it goes under the roller, it gets crushed and reduced in size. And then once it's the right size, the air will use, based on Archimedes' principle of buoyancy, it's just going to lift it up through this. This is actually a dynamic classifier, and that will take it away to the boilers. Now, full-scale mills, for these purposes, combine two processes, not just milling, but also classification. So they reduce the particle size, but then they also select the particle size when it's the right size to leave the mill. And laboratory tests that characterize these mills usually only look at the milling part of it with a set particle size. They don't often include the pneumatic classification. And this can lead to misleading results, particularly for new materials. So one of the main issues that are seen in full-scale mill is something called mill choking. Now, this is your typical materials that are used for bioenergy. And so we've got olive cake up here. This is a residue from olive oil pressing. There's the large amounts of this waste in Africa, the Middle East, and in Spain and Greece. So this is one of the ones that was most used for combustion in the UK over the last 20 years. We then have two here, which are sort of firmly treated biomasses. So we have the top one is a microwave torrefied. That means it's been cooked in an inner atmosphere to remove the volatiles. And that is called almost like a coalification of the biomass. So you're trying to remove the properties more to be like coal. And one of the reasons to improve its grindability. And this one at the bottom is a steam exploded pellet from a company called Zilka, who are an American company. I don't believe they're still going, but this was a lot of interest to power generators about 15 years ago. On the left here, we have coal. This is called La Loma. It's a low NOx coal from Colombia. So this was favored in Western Europe because there was a big drive in the 90s to reduce nitrous oxide emissions from power stations due to acid rain. And a side effect of reducing NOx was also reducing the carbon emissions. So that's why our carbon emissions reduced a lot, was actually to reduce the NOx. So this is very popular, but it's very expensive. But it is a very good grinding coal. It's a subbituminous one. We then have wood pellets. So this is what we mainly import into the UK from America and Canada. So this is what's coming in at 8 million tons. We then have eucalyptus from South Africa, miscanthus, and Ukrainian sunflower pellets here. So these have all come from power generators. This isn't things we've made in a lab. This is what they would be burning actually in a power station. So there are a couple of standard tests that have been developed for looking at milling of coals in particular, but we wanted to see if they could be applied for biomass as well. So this is called a bond work index test, and it's a bit of a beast. It's filled with hundreds of balls of different sizes, and it rotates at around 70 RPM. Now you have the cage around it in case it opens during the process and the balls come shooting out. But it's quite a violent beast, this one. But the test basically works by looking at how many revolutions it takes to go from your pre-milled size to a target particle size. And what you should see is for a good material, it will break down quite easily and you'll get settled to a constant revolution quite quickly. And this is what happens with the Loloma coal that we did. So you can see here we've got two axes. We've got the mass retained on the sieves, we've got the revolution counts, and then we've got here the blue line is the actual revolutions for each run that were calculated to be needed to get to the target size. We then have the purple line is the mass above 1 millimeter. We have the green line is the mass between 90 microns and 1 millimeter, and then the red line is the mass below 90 microns. So the target size we had for this test for coal was 90 microns. And you could see after the first, by run 3, we can see it settling into a pattern of around 250 revolutions. And we've got a significant amount of the material is in the sub 90 micron category. However, when we look at the wood pellets, we see a different pattern emerging. We can see that the rev count continues to increase, and it increases sharply. It's already at 2,000 revolutions by run 3 in comparison to 250 for the coal. And it keeps rising upwards on this line. It takes about half an hour to run 2,000 revolutions, by the way, in this mill. So you can see it's running for quite a long period. And if you think about this is actually relating it to a full-scale mill, if you think about that, that means that material isn't leaving the mill quickly. So you're adding more and more material into the mill, but it's got a very low output compared to the input. And this is called mill choking. You basically, the mill is filling up. The material isn't leaving because it's not reducing in size enough. The target we had for this was 1 millimeter. It wasn't 90 microns, it was 1 millimeter. So an order of magnitude larger than what we had for the coal. However, as you can see, it's not really reducing in size very much. It's struggling to get there. So this shows that there's something happening in the mill that it's stopping that process. It's stopping the material reducing to the size it needs and to have the input and output mass flow rates to be the same. So this is obviously relevant to when you're scaling up any lab scale milling, because to make, and this has been seen for MOF. MOF often is made in ball mills through mechanochemistry. And if you look at the prices for MOF, if they're made with ball mills, they tend to be very expensive. However, if you can move to continuous flow processing, you can bring down the cost significantly, but also the processing time. So one of the spin-out companies we have here at University of Nottingham, which uses hydrothermal processing to make MOF, can make a ton of MOF in 6 hours, for instance, where to do that in batch in ball mills would take weeks. And that makes a massive difference to cost. So any milling process, when you get past pilot scale, if you're going into markets which are not incredibly high value, the consideration has to be is how you move from batch processing to scale up. And this is one of the main considerations, is how long does it take for that material to be processed within the mill, and how do you reduce it, and how do you overcome those issues? So for the biomass pellets, we decided to look more into what was actually happening in terms of the material itself. Now, when we look at a combustion, the residence time in a boiler is set by the Stokes number, and anyone who does CFD will have heard of Navier-Stokes. But the particle size is selected by something called the Stokes number, which is given here. And this is called the cut size, and it relates to the right size to give you the right residence time within the boiler. So your classifier is set up to give you the right residence time. And you can see it's a relationship that relates density to diameter, to the speed of its flowing, and some other material characteristics. And part of this equation relates to something called the shape factor of a particle. So it's not just about its size and its density, it's also about its particle sphericity. Now this is its three-dimensional sphericity, not its two-dimensional sphericity, which can be quite tricky to measure. So what this really means in practical terms is that if you have a round coal particle of 75 microns, and a flat plate-shaped biomass particle of 1 millimeter, aerodynamically, they can both pass through the same classifier setting. And this means you don't need to mill your coal particle to a finer size as the biomass particle if they both meet the right aerodynamic criteria. But what we see in mill choking is even when the particle size is set to 1 millimeter, the particles are struggling to get out of the mill. So all materials have something that's known as a critical particle size for comminution by brittle fracture. When you're in your PhD, you might get asked, "What's the most important paper you came across during your during your PhD?" And for me, it was this one here by Kendall in 1979, because once you've gone past this critical particle size, materials go from being brittle and you being able to use impact as a method to overcome those brittle fractures to ductile. And therefore, those impact fracture mechanisms no longer work effectively. You don't have a fracture mechanism system to take advantage of to break down the material easily. Now, Kendall showed that for coal, this critical particle size was 5 microns. And given that the target for coal is, I think I've got it here, is 70% of the coal should be below 75 microns, you are very far away from that brittle critical size. However, for biomass, this has not been measured, and power generation generally uses a target of 80% of the biomass below 1 millimeter. However, we can see from our testing in the bond work index mill, the mills are struggling to reach that size. So this implies that the critical particle size for biomass is above that target. It's between 1 to 2 millimeters. So you're trying to get the mill to do something. It's a fracture mechanism type of mill, but it's trying to break something down using fracture mechanisms for a material that is not going to do that. And that means you're continuously using this impact, but you're not getting that breakdown of the material. So that means the particle size and shape change is now going to only happen through attrition rather than your impact and brittle fracture. And this takes a long time to happen. Because if you think about it, if you have a particle and using attrition or abrasion to reduce it, what's happening is you're just chipping off little bits on the edge. And that makes the particle more and more round, which helps with the shape factor, but it takes a long time to achieve. Whereas what you have for coal, for instance, is you have this fracturing. So you hit it and you instantly get this sort of explosive breakdown. So this is where you have this difference between compression fracture and shear fracture come into play. And it's very much horses for courses. Is the milling method you're using, if you're trying to get particle breakdown, the right one, the most effective one for that material? Because compression and impact is best for brittle materials like coal, whereas shear factors, so cutting and hammer mills, are better for biomass because they are behaving like ductile materials. So to go a little bit further into this, one of the things power generators and industry really like is sort of metrics. They like if you can sort of consolidate everything into a number that you can then rank things against. They obviously like to know the specifics behind that, but it really helps them with their decision making if you can sort of quantify your work into simple communicatable ideas. So to help with this, one of the things we started to look at is into the milling theory behind mills and linking this energy and the particle size reduction together. Now, there are 3 main milling work indices, and they are all derived from the general comminution energy equation, which was proposed by Walker back in 1937. And what we have here, is we have the specific effective energy. So that's in kilowatt hours per ton. So that's the energy that you took to mill that material for the amount you put in. We have K, which is a material constant. We have your dx, which is change in particle size, and then you have your particle size to the power of b. Now, b is related to the mill that you have. And there's 3 different b values, and they go with these 3 laws of milling. So we have Kick's law, where b value is 1, and this shows that energy is proportional to the log of the size reduction ratio. And this is best fitted to coarse crushing, so jaw crushers, roller crushers, and so forth. We then have Rittinger's law from 1867, I believe, if I remember rightly. So this has been around for a while. And that relates energy to the increase in surface area. So that's most applicable to vertical spindle mills and hammer mills and is relating to fine grinding. This Hargrove grindability index is another standard test that's used for coal. Then we have Bond's work index, which has a p-value of 1.5, and that shows that the energy is proportional to the square root of the surface area reduction ratio. And this applies mainly to tube and bore mills and rod mills, so this is intermediate grinding. But as I've shown, these type of mills are also used a lot in power stations for breaking down coal. So for us to looking at ranking mill performance, we decided to look at the von Rittinger model as it's most related to fine milling, which is what we are focusing on. And it also applies to the mills that we were looking at in industry. And von Rittinger's theory of milling says the energy required for size reduction is proportional to the new surface area generated, and is summarized by this equation here, where you have the specific effective milling energy, the von Rittinger constant, and the feed is x1, and the next two is your product passing size. And we've chosen 80% for this equation. So we use this mill here for a lot of our testing. Now, this is a very special mill. It was made in the 1960s, so it's a museum piece. However, it gets refurbished every few years and is still going strong. There was only 2 of them made in the UK, and we don't know of another lab scale version like this. And what you have, this was modified to replicate a ball and race about 5 to 10 years ago. But we have, the mill is actually just this compartment here. So you can see it here. We have a feeder at the back with a screw feeder bringing in material at this point here. Material will fall under the mill bed and the rollers, and they are operated by a motor at the bottom. We also have this fan, which is pushing air in from underneath, and that lifts the material through the mill, which then goes through a classifier. This can have a dynamic or a static. We've got it set up for static to give it the largest particle size, and then it comes up through the cyclone and then drops out into this bucket here. One of the nice things about this mill is it also has an overflow feature, which means that the material that's too heavy will drop out of the bottom, which means we can see not just what's milling, but what isn't milling as well. So this is a replica, as I mentioned, of Drax. So we did a lot of work with Drax looking at their different types of fuels that they might be interested in. So for instance, they were interested in rice husk as an agricultural residues. And rice husk was great because you put it into the mill and it just came straight out. And this shows the benefit when you get it, you know, what happens when your input feed is the right size and shape and density and just goes straight through the mill. You basically don't need to mill this, and it shows it there. When it struggles, you'll get profiles like this. So this is particle size distributions. So what we have, this is for walnut shell, and we have your pre-milled particle size here in the black line. And then we have the nice fine product here in the blue. And if you only looked at those 2 graphs of what was mill and what came out as a product, you'd be like, oh, that's great. You know, it's lovely and fine. You look at here, the D80, which is, you know, here you're down well below 1 mil. This is going to be great. However, quite a lot of the material came out of the overflow. It was too heavy. It didn't mill. It just got stuck and dropped out. And that's this green line here. And because this was actually over 50% of the weight, when you combine the particle size distributions of the product and the overflow together, your actual milling is at this red line here. So we can see overall that you get a much poorer performance. And if this was a full-scale mill, that overflow would keep going back into the mill. So the rejects get put back in. Our system doesn't do that, but you could keep adding it, but it will, in a normal power station, keep going back in. And it then shows you're getting that mill choking, that the material isn't the input and outputs aren't equal, you're then not getting that effective milling. So we use this for ranking our different types of materials, and I'll come to that in a second. But if we look at the same material in different types of mills, we can see this issue of mill choking a bit as well. And we can see the attrition actually taking effect. So we did a study with 4 different types of mills. So this was a planetary ball mill. This was a Retsch PM100. We have the bond work index mill that I've shown you earlier. We had some cutting mills, and we have our blue ring and roller mill. So these are all very different types of mill with very different types of fracture mechanisms and milling action going on. And when we do them, what we did was we used a piece of software from Retsch called a Chemsizer, which is a particle imaging software. It's non-destructive, so you can pass the particles, your particles through. It will take images with a high-speed camera, and it looks at the particle size and shape, and it actually gives you the 3-dimensional sphericity. Now, what we have here is the average sphericity for these particles before milling, which you could see in this column here, for all the different types of materials. We then have the 4 mills, so we have planetary ball mill, bond work index, knife, and the ring and roller mill. And we can see when you have, for instance, the coal, you can see here there's a slight reduction in sphericity in the ring and roll mill, not much change in the shape from the bond work index mill. But 2 materials we had, which was the wood pellets and the sunflower pellets, choked quite badly in the bond work index mill. And what we notice is that we could see that the sphericity of the pre-milled is less than the sphericity of the milled. In particular for this ring and roller one, you can see it's gone from 0.347 to 0.403. So there's been an increase in the roundness of this material, and we can also see it for the sunflower pellets. It's gone from 0.347 up to 0.382. So we can see that the average roundness of these particles is increasing as in when it goes through mills where it starts to choke. So we could see that as well even more for the sunflower pellets, and I'll just go back. You can actually physically see it with these particle images. So these are typical images for that sphericity that were taken with the Chemsizer. So we can see that we can physically measure that increase in that roundness that happens during these milling processes. And we can see that the actual fracture mechanism is the abrasion and is the attrition, because pellets are made by shredding the material to start with. They're pelletized, and then the aim of your milling process is just to break them back down to the original pellets. So when we look at using von Rittinger, we can take the energy and the particle size reduction ratio to give us a specific von Rittinger rating for each material. And what you see is that it gives you a combined metric. So some materials might not have a huge energy consumption like the walnut, but its particle size reduction wasn't very good either. So that then influences its ranking. And we could see that if we just looked at the product of the milling process, we get different results than if we combine it with the overflow. So for instance, if we only looked at the milled product, we can see that palm kernel material came out best, with pistachio second. With walnut and then pistachio. They're all in low 20s, and the wood pellets up at 32. However, when we look at the milled plus the overflow, suddenly wood pellets gone right to the front and pistachios down at 148. So it's shown a very different performance to the others. Now, rice husk had a very poor result because it has a very low energy, but it didn't really change in size, which shows it actually didn't really need milling. So we can use this ranking to actually assess different materials within that ring and roller mill and see how well they compare against each other. And we've had industry has conducted tests at full scale for the same materials and found that these results correlate. So what we see in behavior if it's good in this mill, it will be good at full scale, and if it's not good in this one, it won't be at full scale. And this gives industry a metric tool to compare different materials. But obviously we provide the information behind that so they can understand why they're different as well. We've also been looking quite a bit at coal and biomass. As I mentioned, we used to be a coal-intensive research institution. However, a lot of our research is helping other countries now that are only starting on that transition to understand the issues that they have. So, for instance, we've been working with Australia, Colombia, and India on looking at co-milling. So that's where you have, say, 90% coal and you add 10% biomass. And this can often lead to issues because you've got two very different materials and you're trying to mill them at the same time. So this is often a starting point for power stations to look at, can they convert their systems to biomass? And what you see here is the milling of a coal. We're calling it 75. That's just the one we had. And you can see here, this is the pre-milled size and this is the post-milled size. So you're getting a huge particle size reduction through the milling process. This is the milling profile for palm kernel. So you can see we have the palm kernel original is here, it's called PKS, and it's very coarse. We then have the milled, which is nice and fine, but we had a significant amount of overflow, which then gives us this composite one in the middle. Now, it doesn't mill well on its own, palm kernel shell. Every time it would just choke up the mill and it wasn't really liking it. However, we did co-milling tests at 10 and 40%, and we found that there was a synergistic effect, and that if you milled the palm kernel with the coal, the palm kernel didn't choke anymore. You always got complete milling. So we could see that combining different materials with different material properties, one being brittle, one being ductile, can actually improve the overall milling. Now, the particle size distribution you get out is coarser than what you would get just with the coal. So that obviously has a knock-on for combustion. But there are benefits for co-milling different types of materials together to see how to overcome some of these choking issues. One of the other things we've been looking at as well is we often look at industrial issues. So what we have here on the left is a screw feeder from EDF Cotton, where they were trialing co-milling olive cake. Now, olive cake is, as I mentioned before, is a residue that's used from olive oil pressing. And what was happening as it was going through the screw feeders, it was forming this solid cake here, and they were having to use jackhammers to get it out. It was like concrete, and they were having to replace the screw feeds on a very regular basis. And as you can imagine, that's not economically sustainable. So they observed this severe caking within the screw feeds and asked us if we could replicate it in the lab, or if we could, to look into it a bit more. So we took some of the olive cake and put it into a PM100. And as you can see here from the ball mill, we replicated the sticky cake on the side. Now this, apologies. So you can see here it was actually a very solid cake, and you actually had to chip it off with quite some force. And it was stuck to all the balls as well. And when we looked at the composition, the particle size distribution of the olive waste, you can see it here. It's composed of 3 parts. So we have these agglomerations and pips and pellets that are here on above 3.35 millimeters. We then have this midsection, which is the pips or the olive stones that you get. Because if you think about an olive, it has a stone and then it has an outer fleshy layer. And that fleshy layer is the pulp, which comes below 1 millimeter. So this is fine material. So you have this 3 different parts to the material. And we wanted to see what was happening with each of them. So we looked at the influence of moisture. So we dried it and ran it as received. And we found that it was only caking when it was wet. So we thought, what kind of issues cause stickiness within the food industry? Because at the end of the day, olives are a food. And we then decided to try and use differential scanning calorimetry, so DSC, to see what was happening around the glass transition zone. So we put the material in, and we found that there was a glass transition step happening around between 80 to 100 degrees. And this caking was being brought on by the step. And you could actually see the heat being generated in the mill through thermal imaging. So we can see here that those actions, we're seeing a lower heat generation within the mill when you're using the wet material than you were when you have it dry. But we also found we milled each section of the olive. So we milled the pulp, we milled the pips, and the pellets individually for the same conditions, and we milled them as a whole. And we found that the caking was only really happening in the pulp section of the olives. And this was due to the high sugar content of the olives itself, which is actually variable by seasons. But by drying these olive residues, you could actually remove this caking issue. So moisture content was key to overcoming the caking of the olive residues in the industrial plants. So the relevance to mechanochemistry is understanding the material properties at a macro scale can help us understand what's happening when we see these caking issues and so forth, and how it can relate to milling conditions, and that can show us why these issues occur. So some of the recent work I've been working on in relation to mechanochemistry has been looking at opportunities for extracting high-value products from seaweed. So the UK used to have quite a buoyant seaweed industry, primarily for potash production, but that has reduced over the last century, and it's now mainly used for food processing. But if you think about seaweed, it's about 80–90% moisture. And the current issue is you get the seaweed out of the sea and then it starts to rot basically pretty quickly. So they have an issue that they can only collect it at certain times of the year. They get a large volume. They then have to dry it, which is energy intensive, and then they need to shred it before they can process it. So the research drivers for this work is basically, can you actually start combining those processing steps of particle size reduction, removing the water out of the system, and actually doing the extraction processes that they want to do in one step? So I'm currently working with a Scottish seaweed company looking at the extraction of biofuels and chemicals. And I had a short project with a student this year who did some exploratory work looking at the extraction of ficoidin, which is a sulfated polysaccharide, which is found naturally within the cell walls of brown seaweed. And this is used in dietary supplements and cosmetics and functional foods, and it's heavily researched for its promising bioactive and therapeutic properties. The one we looked at is a Scottish seaweed, and it's called bladderwrack, which you can see. This is what it looks like, and you see this a lot in the UK coast. And what we did is looking at blended milling combined with hot water extraction. Now, we used FTIR to show that ficoidin was not visible in the pre-milled material, but became more visible in the solid portion with milling and hot water processing. So this is the FTIRs of the different processing steps. And we can see that you don't see it at the start, but then as you actually mill it, and we found actually heating it, the water as you milled it, made the ficoidin actually more visible than if you just heat it and then mill it. So the student did a lot of exploratory work and saw that we could actually start seeing the ficoidin was there, whereas it wasn't before. And the mechanical processing improves the exposure of the functional groups by disrupting the seaweed structure. We're currently doing more work into this, exploring how we can use solvents in situ to actually start extracting the ficoidin and other compounds into the liquid phase. So in summary, what I've learned from all my milling experience is that it's very much horses for courses. And when we're looking at any milling process, part of the consideration needs to be, is the milling process that you're using, be that bore mills or hammer mills or cutting mills, are they the right ones for the material that you're looking at? because how can you optimize it through the fracture mechanisms that you're using? Is there potential to link activation energy to the milling conditions themselves, the time, the speed, the volume, and the macro scale milling theories that we are used so much by industry? And based on this, is it possible to combine milling theory for the material extraction, which links yield with the milling energy, mass, and particle size reduction? And these are all questions for myself as much as anything else. And then obviously, coming back to a lot of the theme of my talk is the continuous flow issues. Problems have often been seen in other sectors, and there is a large opportunity for cross-collaboration here, but also learning from what's happening. As I mentioned, milling is 2 to 3% of the world's energy. It's a well-established technique, and it's done at scale everywhere. So as we scale up mechanochemical reactions, are there systems that are already existing that could work for these different applications? Because there's a whole industry that uses milling, and it could rapidly advance that scale lab to full scale production by taking advantage of those systems that are already in place. So I'd like to thank you for your time, and I've put up my LinkedIn profile if you want to connect, so please scan that if you would like to. And if you have any questions, thank you, please ask them now or send me an email. Thank you.
Thank you for that presentation. We do have a few questions from the audience. Let's start here. First, does the surface roughness of the particles affect the process, or is this captured by shape?
I think for these materials, they are very quite rough. I think it depends what a scale of roughness you're talking about. It would be as much to do with whether they're brittle and ductile, I think, and now those fracture, you know, the deformation and the opportunities for fracture, are they exposed? For instance, if we look at coal, it's got a fracture structure mechanism on the surface, so it's where those imperfections are in the materials. So if your work's looking a lot of reagents, then that would be less than it would be, but there's always imperfections in every material. And it's understanding how perfect or imperfect your material is will influence, obviously, those activation energies, because the further less perfect they are, the more energy you'll need to break them down.
Thank you. So next question is, you mentioned compression and shear have different effects on different types of material, but can these processes ever be decoupled in a mill?
What do you mean by that? Apologies. I mean, so from the perspective of the mills, if you think of what's happening in a ball mill, that is an impact collision. So that is fundamentally what is happening within it. You've got a ball moving around and that's hitting into things. That's an impact. And if it's brittle, that impact is going to cause it to go through those fractures and then explode. Whereas if you're using shear, it's often a knife mill. So you've got this cutting action. So you've got a sharp edge cutting through those materials and slicing it like a knife. So that is fundamentally what the mill is doing. So in terms of decoupling us, I don't see how you could, because that's what a mill is.
Makes sense. Thank you. All right. Do you think there are chemical reactions going on as well in the coal or biomass mills, or maybe the seaweed?
Oh, absolutely. And we could see that from the olive cake, because you could see that happening through the glass transition. You're getting a change in state. It's going from a loose powder into a solid material. There's something happening there, and that's it. That's a chemical transition. And that's what we want to figure out in the seaweed is, can we combine that solvent extraction with milling to extract those high value compounds. Now, even if it's just so that you can reduce the amount of processing steps, you might need further processing to, individually extract them in the liquid phase. But if you could do that as a processing step rather than drying it, which is the most energy intensive part of many processes, is the drying energy. That's where most of the carbon emissions are. That's where most of the cost is. So if you can remove that step and process things quicker, it means you could separate out the high value compounds into that liquid phase And then you've got the solid phase, which you can then use for another process, or you can use it for lower value valorization options. So that's the idea with the seaweed extraction, is to actually do that process all in one kind of thing, to reduce the amount of steps and do those chemical reactions at the same time.
Got it. Thank you. All right, let's do one more. What are the considerations when applying or scaling up the findings from the spindle mill to the larger scale industrial mills you showed in the beginning?
So obviously, one of the considerations is you can't take the exact energy, because we get, I measure it with an energy meter, and I can't say that process is going to use that amount of energy, or it's going to give you that exact particle size reduction, because they are not set up the same. My mill doesn't have variable speed flow, so I'm only working out one flow rate, and that might not be the flow rate that they have in the power station. So there are all those variables which are not the same. However, it's those trends that we can see that have been shown. The power generators have shown themselves. They've done trials in Germany for the same materials. We milled hundreds of different types of refuse-derived fuels. I don't know if you've seen those. It's where you have basically recycling waste. They shred it, and then they make pellets out of it, and then they combust it. And we did a hell of a lot of trials milling it up and then looking at the different size fractions, and then using thermogravimetric analysis to look at what's in each of those size fractions, so we could see where the paper was going, where the plastics were going, where the aluminium was going from crisp packets and so forth. And the company we worked for that was doing that took our results and then selected a few to do full-scale trials, and they found that the results correlated well. If it was good in our mill, it wasn't good in it was good in our mill, it was good in the big mill, and if it wasn't, and so this is what I mean about providing industry with metrics, in the sense it's more about a ranking. They understand that it's not going to be exact, but they can take that learning and apply it for strategic commercial decisions, for instance.
Great. Well, thank you so much for your presentation. We really appreciate it.
Thank you.
Thank you, Professor Williams, for that outstanding presentation. And thank you so much for joining us. Just a reminder, we have an amazing group of seminar speakers over the past several years, and they're all available to watch anytime on the YouTube channel. We also want to hear from you. If you have any suggestions for improvement, please do let us know using this QR code or send us a contact anytime. Lastly, we have some great speakers planned for the upcoming months, and we hope that you will join us for all of them. Thank you again.